Hello dear learners. So are we ready to learn the chemical properties of ethers in this particular video? I've classified the chemical properties of ethers into three categories. If you remember, I've already given you the flow chart to depict the chemical properties of ethers, and I'm quite hopeful that you have kept it on the side of your table so that you can refer to this flow chart while we are writing the reactions down in today's lesson. If you are new to the channel, you are on Pen and Paper Chemistry on YouTube, and here we cover topics related to chemistry for grade 11 and 12, and a compulsory condition for attending the videos on this channel is pen and paper. So a pen and a notebook will go a long way to give you the confidence in chemistry. So please make sure that you have these in place. If you've missed the previous videos, we are presently covering the topic of ethers. We have already done the preparation and the physical properties of ethers. In today's lesson, we are continuing with the chemical properties of ethers. Three categories of chemical properties. Now, first of all, we need to understand that in the case of ethers, R, O, R. There are two alkyl groups on both sides of oxygen. And what is the nature of the alkyl groups? Yes, they are electron releasing. And my poor oxygen is already loaded with lone pair of electrons. So it is in no mood to show any kind of further reactivity. So if you talk about nucleophilic substitution reactions, no, they do not easily undergo this. It is very difficult to break this particular bond in order to cause substitution. So that means if nucleophilic substitution reactions are less, we will have to do very few reactions involving the cleavage of the CO bond. But look at the poor oxygen. It's loaded with lone pair of electrons. It will have a tendency to share this lone pair of electrons with some species which is hungry for electrons. That means some species which is carrying a positive charge, right? And the easiest species that we can find is a proton, H positive. So the second set of reactions that we will be talking about are the reactions on the ethereal oxygen, the oxygen with a lone pair, with two lone pair of electrons on it. The third category of reactions is very typical of aromatic compounds, and those are electrophilic substitution reactions. We have covered the mechanism, the details of electrophilic substitution reactions in quite a few topics. If you remember, we've done them in benzene, we've done them in phenols, we've also done them in haloarenes. Yes, these are the topics which have already been covered on the channel. Let's start with the first one then. By the way, keep writing this down. This will be very handy for offline reference. These are your notes all compiled in one place which you can refer to when you are offline and you are preparing for your examinations. Something written in your own hand will go a long way to give you the confidence. Reactions involving ethereal oxygen. So as we discussed, there are two lone pair of electrons on the oxygen atom, and because of these lone pair of electrons, it can be an electron donor, in which case we call it as a Lewis base, Or it can also be a proton acceptor, in which case it's a Bronsted base. So all in all, our ethers are basic in nature. Right? They react with mineral acids. Now we know that bases react with acids to form salts. So they react with cold concentrated mineral acids to form a product what we call as oxonium salts. Interestingly, these oxonium salts on hydrolysis treatment with water give us the ether back. Now let us try and break down what is this oxonium salt. So C2H5O, C2H5, that is our ethoxyethane, lone pair of electrons on the oxygen, the proton coming from the acid, and we have C2H5O, a lone pair of electrons being shared with the, hydrogen from the acid, and we will have C2H5. Can you please calculate the formal charge on the oxygen atom here? Please calculate the formal charge on oxygen. We have already done calculation of formal charge under the topic of Lewis structures. In case you are confused about that, you can visit that video a little later. Very good. It's a positive charge. Now this positive charge, because I've written a bracket, what I will do is I'll put this positive charge outside the bracket. That means this is a charge carried by the entire ion, balanced by the negative charge of the chloride ion. In other words, what have we got over here? This is what we call as an oxonium salt. Salt, in the end of that, an ion in that salt is chloride, and there are two ethyl groups in this. So what do I call it as? Diethyl oxonium chloride. And interestingly, on heating, it will give us the ether, by hydrolysis. On heating, it actually gives us the alcohol. So on hydrolysis, it gives us the ether back. Now I've been using the word oxonium again and again. Does it sound familiar to hydronium that you've been studying in your previous classes? Remember, hydronium ions, acids release hydronium ions. What are hydronium ions? Hydronium is HOH is our water, and then when this combines with another H, and this becomes positive. So look at the structure here. O carrying a positive charge bonded to three other atoms. That is what gives us an oxonium. That means oxygen carrying a positive charge, forming three bonds. You may write it down for referring it later on. Okay, so this shows the basic character of ethers. Let us now move on to the AutoOxidation of ethers with oxygen from the air in the presence of light. Now, if it's in the presence of light, what does it tell you about the type of reaction? Yes, it would be a free radical. Remember, we spoke about free radical substitution reactions and so on. It is with oxygen of the air. That means it's an oxidation reaction. Obviously, ma'am, what is the big deal about it? Yes, of course, we are carrying it out in the presence of light. So that means light, metals, aldehydes, they can catalyze such kind of reactions. what are we going to form? That's the big question over here. Auto-oxidation of ethers gives us what we call as peroxides. Peroxides means having the linkage O, single bond O attached to other two groups, right? What kind of peroxide will be formed here? I'm going to spread out my ether. CH3, CH2O, CH2, CH3. Now see here, the carbon which is attached to the oxygen, this gets oxidized. So let me spread out its wings more, and I have a hydrogen and a hydrogen attached to an oxygen. This gets oxidized by the oxygen of the air. That means even lower concentration. You don't need to have pure oxygen. In the presence of light, what does it give you? CH3. Now the CH bond here gets oxidized. So we will have C and a peroxide linkage, OOH. So hydroperoxide. The other H remains in place, OCH2CH3. This is named as, would you like to try and name it yourself? Go ahead. 1, 2. So at the first position, I've got an ethoxy group, right? So 1, ethoxy. Now, this is an alkyl group. Which alkyl group is this with 2 carbon atoms? Yes, it's ethyl. And what do I have? I have hydroperoxide attached to the first carbon atom. So this becomes hydroperoxide. So you notice over here, the oxidation is taking place at the carbon which is attached to ethereal oxygen. Drawn the structure, written it down. Now, these peroxides are actually very, very dangerous. They are explosive in nature. That is why we never distill the ether to dryness. If we distill the ether to dryness, our peroxides have higher boiling point than the boiling point of the ethers. So the ether will distill off. With the result, what will happen to the amount of peroxide in the flask, distillation flask? Yes, obviously the amount is, or the concentration is going to increase. Greater the concentration, greater the risk. That is why, especially ether, which has been kept for a long time, should never be distilled to dryness. And we never store the ether for a long time. When we have to use our ether, we have to be careful that the peroxides are not there. How do I check whether my sample of ether has peroxide or not? What do is we take the sample of ether, we treat it with aqueous ferrous sulfate, followed by treatment with potassium thiocyanate. Appearance of blood red color shows that the sample contains peroxide, and I have to be very, very careful. It is because of the dangerous nature of the peroxides, usually ethers are avoided for use during industrial processes. I hope you have written all the points down. Okay, one question here. In the previous reaction, I wrote the reaction of ether with HCl, but if you notice, I have also given that it can react with cold concentrated H2SO4. C2H5O, that is ethoxyethane plus H2SO4, cold concentrated. What will be the products? Please complete this reaction. Try writing it down. Look at how I have broken down the H2SO4. That should give you a hint. Go on copying. So first I wrote C2H5. Well done. O, lone pair of electrons bonded with hydrogen. C2H5. One lone pair remains, overall positive charge. Oxonium ion. What will be the corresponding negative ion? HSO4 negative. How are you going to name this compound? Diethyl, yes, diethyl. Oxonium, yes, because my oxygen is carrying a positive charge. Here I have chloride. Do I have chloride here? What will it be? Bisulfate or hydrogen sulfate. Diethyl oxonium bisulfate or hydrogen sulfate. The next set of reactions that we are going to cover are an example of nucleophilic substitution reactions in the case of ethers. Now, as we said earlier, our ethers are not very happy with breaking the bond and being replaced by another nucleophile. So it should be a very strong nucleophile which should convince the ether to break down and be replaced by another atom or group. So what are those nucleophiles which are able to bring about this kind of substitution in the case of ethers? We shall talk about it in the next video because we've got to cover a lot of mechanisms as well in that. So stay connected as we go on to the next video.